expand to make it a little more difficult. So we are implementing projects based upon these two papers, the XNOR Net and Binary Connect. So the main difference here, the XNOR Net specifically, we're working on a binary neural network with the binary inputs and the binary weights. With the Binary Connect, we are making a design using floating point inputs and binary weights. And the goal here was to develop binary neural net architectures, and we're going to focus on the feed-forward operation. So taking inputs, going through the network, doing the operations upon the weights, the inputs and the activation function, and propagating that to an output. And we're going to investigate fully connected and potentially convolutional layers. So this is an image of one of the papers. Specifically, this is one of the convolution operations, where in this case it's an image. So say it's like 100 by 100 pixels. You're taking a smaller subset of that window and moving it around. And you can see here for the binary weights, the floating point inputs, you can see floating point inputs, binary weights. And then for the XNOR Net, you have the binary inputs and the binary weights. And then we'll describe in a little bit more detail how we're going to implement each of them. So for the XNOR Net, this is the simpler one, the binary inputs and the binary weights. We're going to design XNOR blocks specifically for the fully connected layers first in HDL using a mixture of Verilog and VHDL. So our team members are familiar with, or each more comfortable in different areas. And then after we design the XNOR blocks, we're going to investigate designing one for a convolutional layer as well. And then also designing one of the pop count blocks. And then we're also implementing test benches with each of these little building blocks. And we're going to create a test bench in Python or some type of higher level language so we can check our math. So we'll know what the inputs are, we'll know what the expected outputs are, and then we'll have a way to verify that our HDL logic simulations give us the correct output. And then the final step is to simulate the test bench. So the next slide, did you want to talk about this one?
Sure. So the next slide, we'll be doing with floating point inputs, binary weights. The conversion from floating point to the binary thing, we have planned for now to do it in HLS, which will be in C. And then we'll be reusing the components that we made in XNOR Net for the fully connected layer and the convolutional layer. I think there will be some overlap for that. The pop counting thing and the XNOR thing would probably be the same, and we'll be using that. For the test benches, though, we'll be, for the starters, we'll be generating random numbers. We'll use the test bench by using some Python code so that we can check the math that we do on the FPGA simulation by testing it with the Python results for the multiplication and the addition. But the ultimate goal would be to test it with a neural net using PyTorch in Python. But at this moment, our team's not sure whether we'll be having that time to implement a whole neural network on PyTorch and doing a comparison how the binary neural network will have its effect with a complete neural network implemented on PyTorch. So we will be attempting to do that, but that's not part of the proposal as of now. These will be the deliverables for our project. There will be PDF reports and simulation results, along with the Git repo for both HDL and HLS. This is the backup slides for the convolution part, where we'll be inputting 1,000 images of 10 cross 10, and the kernel size would be 3 by 3. So each time the storage space inside the FPGA would just be of 9 bits for the 3 cross 3 data block, and we'll be implementing an XNOR plus pop count thing, which will be the multiplier. and then running the sum for it. And that's
Back to the first one. Next. Okay. So you are in charge of the design of XNORNet, right? And I would like to remind you that maybe for the first layer, XNORNet need a multiplier. You need to do some multiplication for the first layer. So
Okay.
you also need to design a multiplier in this slide. And a fixed point, not floating point, fixed point multiplier.
So is that because the inputs would be the fixed point number?
This is the feature of the first layer of the XNORNet. Please read the
Okay.
paper. Please read the paper. And I know that you know what you are talking about. Next slide. And this slide, you are in charge of the binary connection, right? Mm-hmm. And I know that you don't know what you are talking about. Because the binary connection does not require XNOR block. It requires adder, only adder.
But I was reading the paper. It said that once you connect the floating points to binary, you can normalize the weights too. And
Yes, you
that's
can
why-
normalize the weight, but you cannot normalize the input. The input is still fixed point. It's not a floating point input. I don't expect that you can do some floating point stuff. Just fixed point.
All right.
Okay, modify this slide.
All right.
Make sure you read that binary connection paper. Okay, I don't think you read it carefully enough to understand that paper.
Is the,
How about yes?
so our plan was to design something for the feed-forward operation. Is that sufficient?
Yes.
For
Yes.
this? Okay.
And you don't have the responsibility. Who did what? Who will do what?
Mm-hmm.
You should add that slide.
Okay.
Who is in charge of what? Before you upload this one to the web page, to the
Okay.
canvas. Modify this slide. This slide has a lot of things you cannot do. For example, the floating point input. You cannot do anything about floating point. Floating point representation is very complicated. Floating point adder is very complicated. I don't expect you can do that. Just fixed point.
Okay. So we were thinking of 1-to-1 precision, which was 32 bits, but yeah, we'll add the fixed
Okay.
point thing.
Okay.
Okay.
Any question? If not, the second group, please.